Okay, good morning, good afternoon, good evening to all of you. I know you're joining all over the world. I'm Ioana Petrescu. I'm a global fellow at ESPI, and I am absolutely delighted to welcome you to the second session of the Space Economics Seminar, which is organized by ESPI, the European Space Policy Institute in Vienna, and by the Ownership Project at Harvard Business School. Last time we were thrilled to have over 80 participants. It was really a great surprise to us that there is such a great interest in this new field. So we're curious how many we are going to have today. Before I give the floor to our speaker for today, I would like to repeat the seminar guidelines and maybe just say it for the first time for the ones joining us for the first time today. So first of all, keep your microphones muted unless you are called on. We expect a large number of participants, so we just don't want to have a chaos in here. If you have questions, please write them in the chat first. Then after the speaker finishes his presentation, which will last about 30 minutes, I will call on participants and let them ask their questions directly, and I'll just go through the chat. Please do not interrupt the speaker during the talk. We have a large audience and we want to give everyone a chance to listen. The session is being recorded, so we kindly ask you to complete the consent form if you haven't done it already. I did send you a link to the form when I sent you the reminder last week. So it's extremely important because we will make it public. So if you speak or your name shows up, we want to have your consent on that. So, and obviously we encourage questions that are related directly to the paper and its argument. So just keep it a question or a comment about the paper. So with that, I will present to you Ely Sandler. And Ely, he's a fellow at the Harvard Kennedy School. And Ely is working on energy economics, on climate finance, and outer space policy. He teaches the course, which is called Financing the Green Energy Transition. And he's also teaching a seminar on outer space governance at the Harvard Kennedy School. Outside his academic work, Ely is a partner at Aurelia Foundry, a leading early-age space tech venture capital fund, and the managing partner of Article 6 Group, an infrastructure finance firm building large-scale green energy projects all over the world. He will be presenting a paper today, which is called Reevaluating Space-Based Solar Power as a Dispatchable Power Resource. And this paper you can find online on the SP webpage. We uploaded it and we encourage you to read it. And in fact, we are encouraging all our participants to read the papers before the seminar, such that to make sure that we have a very constructive discussion. Ely, I give the floor to you, and you have 30 minutes, and then I'm going to open to questions. Thank you very much for accepting to be our second speaker for this semester.
Great. Thank you so much, Joanna. And it's great to see everyone. So, as Joanna mentioned, my background is actually really not so much in space. So I've worked for a long time in energy and energy finance. My first job was at Morgan Stanley, basically doing energy funding. And maybe 3 or 4 years ago, I started working more on space policy. And the way I got into it is via this thing called space-based solar power. And so the paper I'm going to present, and I'll share my screen in a second, is basically me trying to come at this question of space-based solar power not from an engineering one, not from kind of a technical side, and also not really from a space policy perspective, but from energy economics and trying to think about what is the problem that we're facing in the grid today, and how can this potentially new technology help solve it? And I hope it's kind of a new perspective on space-based solar power. I'm going to assume that people haven't done any work on it before, so I'll start from basics. So as I mentioned, the paper is called Space-Based Solar Power as a Dispatchable Power Resource. And so as background, in energy world, there's something huge happening in the grid right now, particularly in developed economies like the United States, but all over the world, which is that we have a huge amount of increased demand for electricity. This is just one of the predictions. There's many, many ways I could show it. But basically, electricity demand, you see this in terawatt hours, which is the unit of electricity, has been roughly flat for the last 20 years. Same with peak demand. So at the peak of the day, let's say when everyone's turning on their air conditioners, we haven't really had any electricity growth for nearly 20 years. In the United States, for example, we build about 1% of our transmission lines gets added every year. This is a very, very small churn, and that roughly correlates with adding new electricity to the grid. However, in the next 10 years, this is going to explode. And this is driven by a few things. If I was giving this presentation 2 years ago, it would have been all about climate change. I teach climate finance at the Kennedy School. Really broadly speaking, the way to decarbonize an economy is to do things with electricity that you're currently doing with fossil fuels. So that could be driving your car. So you switch from a internal combustion engine to an electric vehicle. That could be the way you make steel. You switch from coal reduction to an electric furnace. But in general, we need to move things from fossil fuels onto the grid. And we need to have the grid be powered by renewable energy rather than by fossil fuels. So this first mega trend is decarbonization means that the 2/3 of the economy that's currently fossil fuels, not electricity, that moves onto the grid. But at the same time, now because of data centers, which are currently maybe 2% of US electricity demand, that will become 5% by 2030. So that's more than doubling in size. This is going to end up being a huge part of why we need electricity. So first point, we need way more electricity in the United States and elsewhere. This is just another example. This is UX electricity sales going up in commercial, industrial, and residential. And you can see the commercial is the largest. That's basically data centers. Lots more electricity needed. Now, the problem is, and this graph is a little bit small, but this is kind of the best I could see. There's this challenge that we're facing in electricity world, which is that as the percentage of electricity from wind and solar goes up, in almost every country in the world, and in almost every state in the world, in the United States, the price of electricity also goes up. Now, this is a correlation, so it's not a causation, but in general, as you increase solar and wind penetration on your grid, the price of delivered retail electricity goes up. This is like slightly counterintuitive, so I want to explain why. It is definitely true that the cheapest way to generate electricity in almost every market in the world is with solar. The cost of solar is probably between 3 and 5 cents per kilowatt hour. This is crazy cheap. I live in Massachusetts. The cost of electricity here is about 45 cents a kilowatt hour. But the problem is that that is the marginal cost. So when the solar panel is producing electricity, it produces it at 4 cents a kilowatt hour. But imagine you have a grid with 40%, like here, or 50%, or in the case of Norway, 60% wind and solar. If you have 10 days when the sun and doesn't shine and the wind doesn't blow, you need to make sure you can deliver electricity, which means you basically need to build into your electricity system an entire backup grid. You need to build gas peaker plants, you need to build batteries, you need to build capacity markets. So you essentially double the amount of capex you have to have because you need to build in the capacity for 10 days or 15 days or however long that stretches for when you do not have the sun shining and the wind blowing. You need to be able to produce electricity. And so you add a lot of capex to the grid as a backup. And at the same time, on those days when you have to, let's say, use a gas peaker plant, so you don't have the sun, you turn on your gas plant, that gas plant has to charge you an outrageous amount of money because it's not being utilized, 300 days of a year. And so they get to charge you a really, really high premium. And so in these markets with really high electricity prices, often it's because the utility ends up paying a crazy amount to fossil fuel plants for 1 or 2 days a year just to maintain stability. And so this is the problem we're facing in electricity markets. Massive growing demand for electricity. The cheapest thing to put on the grid is renewables. But we end up, even though it's marginally cheap, we end up increasing the cost of electricity. Now, as I said, this is the correlation, so I don't want to overstate this. There's a huge amount of academic literature, which I cite in my paper, really trying to understand where this comes from, and it's not super clear. But this is an example. This is the California grid, and this is the US Northeast grid where I live. The California grid has much, much, much more solar than the US Northeast grid. So CAISO, the California grid, is at 30 or 40% solar. And this is what's called the firming cost. That is the amount the utility is saying that they're having to pay for gas peakers, capacity markets, and backup markets. And you could compare that to the Northeast, where there's much, much less solar energy. That firming cost is less than half, basically because they don't have to compensate for the variable renewable energy. You'll also notice that this says PV, photovoltaic plus storage. So actually, like a lot of this cost is storage. So if I mentioned a photovoltaic cell can generate electricity about 4 cents a kilowatt hour, the levelized cost of energy. So that would be about here. But all of this, that's the cost of adding batteries. And then all of this, that's the cost of these gas peaker plants. And so basically, we need a solution to not have electricity costs go up as we add more and more solar. About 90%, a little bit less, of new electricity generation in the United States is solar. So we need a solution. Now, this is what brings me to space-based solar power. I'm going to explain briefly what it is and then how I see its role in the grid versus what the kind of traditional conception of this is. Space-based solar power, most people think of it as having come about actually in Isaac Asimov's fiction. So in like 1910 or 1920, he wrote a sci-fi story about space-based solar power. And since then, people interested in space have been like talking and thinking about space-based solar power for a really long time. The philosophy is pretty simple. You basically put photovoltaic cells in space. They capture solar radiation. Because there is no atmosphere, the amount of radiation you can capture with the photovoltaic effect in space is double or triple. And so you can get way, way, way more energy onto, electricity generated, even just with a normal solar panel. So you've got all this electricity that's being generated in space. You then beam it down to Earth. So this basically converts the electrical current that's created by the photovoltaic effect into a microwave, which is beamed down to Earth. Now, it sounds kind of scary. You're beaming microwaves to Earth. This is a very similar technology to Wi-Fi. So Wi-Fi is a very, very light microwave signal. And it's powerful enough to give information, but not powerful enough to power anything. This is basically the same principle. You would transfer energy from space to Earth. You would then capture that microwave energy and convert it back to electricity. The way you capture it is basically with a giant antenna. It's called a rectenna because it's rectifying, so it converts it from an alternate current to a direct current. I can get much more into the physics of it. I'm an economist by training, not a physicist, but I've learned to understand it pretty well. And then you transmit it and you distribute it back to houses. So this is kind of the idea of space-based solar power. Again, we can go more into how that works, but I want to get onto the economics of it because I'm an energy economist. Now, there's been, over the last, let's say, 5 years, a huge amount of growing interest in space-based solar power. On the screen, what you see is like all of it's a bit too small for you to actually understand, but the yellow is where papers have been published. So Europe, Russia, China, the US, Australia, everywhere is publishing papers. Green is there are actually private sector companies trying to do this. As Joanna mentioned, I'm a partner in a small early stage space tech VC fund. We've invested in a space-based solar power company that I know of. There are basically 6 really serious companies doing this. One of them was founded by the founder of Robinhood, and they've raised about $70 million. Like, this is serious money. And then the purple are actually kind of national security or national lab type experiments. So these are experiments that are actually being done, either trying power beaming over long distances, which we know is theoretically possible. It's just about calibrating it, or seeing if you can target a beam from a satellite well enough to hit a receiver. So lots and lots happening in the world of space-based solar power. This is being driven by a few things. I think everyone on the call, if you're interested in space, probably knows this graph really well. But this is a log scale of the decline in launch costs per kilo, which I find just astounding. So in the shuttle era, you're talking somewhere between $40,000 and $70,000 a kilo to get to LEO. Once SpaceX get involved, this falls to about 1,200, something like that with the Falcon Heavy, just under 2,000 with the Falcon 9. So that's like a 96% drop in 10 years. Remember, this scale is log, so this is going really, really quickly. And then Starship is selling cargo, and in theory, it will launch next year, probably more likely 2027. at $200 a kilo, which is the same as if I were to overnight FedEx something to California. So Starship is selling um, ability to be on a launch to Leo are the same as if I wanted to get something overnight on FedEx to California from Massachusetts. So this is the first thing that's catalyzing interest in space-based solar power. It's like phenomenal decline in launch costs, which means we can put things in space. Um, the second thing is just we're getting very, very good at engineering. So because we've put so much stuff in space in the last year, we're just much, much better at understanding how orbital dynamics work, kind of remote rendezvous, unfolding of satellites. Something that astounds me is that in the last year, 70% of the stuff in space, it got there in the last year, which is just, again, these facts astound me. And then the third thing is the growth of private venture capital and commercial interest in space. So this is basically investment in the private sector. I probably should have updated this, but basically since the kind of the SPAC boom, things have gone down a little bit since like 2020, but you've still got billions of dollars of private money being invested into space. And then before I get into just the kind of the meat of the paper, I work on clean energy generally, and in the last administration in the United States, we had a lot of engagement with the White House on the IRA. As you might imagine, the current administration is much less interested in talking to Harvard University about clean energy than their predecessors. However, they are very, very interested in United States dominance in space launch and in the space industry. And if you think about what is it that could provide limitless demand, like really limitless demand for launch services, it's probably either telecoms, which is Starlink, and that's what's happening now, or it's energy, and it's the ability to generate power in space. Everything else, we invest in them: space manufacturing, biomedical sciences, etc. There's a lot of things you can do in orbit, and they're very interesting. But really limitless demand that will only come if you can do energy from space, because the terrestrial energy market is so big. So serious work is being done on the economics of space-based solar power. This is from a NASA paper that came out in 2024. And they basically took two relatively well-studied concepts of like literally how you would do this. And they ran a really, really in-depth techno-economic analysis. So one is it's called a heliostat swarm. You basically send up lots of little panels. You have them self-assembly in space using electromagnets, and then you concentrate the power. The other is a planar array concept. And so it's in some ways significantly simpler. You send up these huge planar arrays and you reflect the light down, or not light, you transmit the energy down. There's kind of pluses and minuses to both. The paper is excellent. It's linked in my paper. I would actually suggest reading it. It's just very, very interesting to see how they think about these engineering concepts. So they evaluate what kind of cost of energy you can get to. The standard unit of cost of energy, and this is what I was using in those previous slides, it's called levelized cost of energy. Basically, like how much does it cost you to produce 1 kilowatt hour of electricity on Earth? And this is one of their key tables. They get to an LCOE, so a levelized cost of energy, of about 60 cents, between 60 cents and $1.50 for the baseline. So they're saying like, basically today, like if you could do this today, or really with technology we know is coming in the next couple of years, like they do use Starship instead of a Falcon 9, but they think that like a realistic estimate for what we can deliver energy at today is between 61 cents and $1.59 per kilowatt hour. Now, as I mentioned, solar energy is about 4 cents to generate, maybe 12 cents if you include the cost of batteries. Gas peakers generated about 20 cents. Nuclear power is kind of all over. It could be up to 30 or 40. Some estimates think it's 15. The point is that this is significantly above current energy generation costs. With a lot of different things, kind of flexes and changes, and we can go through these kind of cost of launch, orbital transfer. So all of these things have to be in either geo or highly elliptical orbits. And so at the moment, the only way to get from LEO to GEO is to have a spaceship take you there, which is very expensive. If you could have electric propulsion, so your satellite moves itself, this would go down in costs. They think that maybe they could get to 0.4 to 0.8. That is assuming like every single cost comes down in a way that I think is somewhat unrealistic. And so this is basically where they get to. They have all of these different sensitivity analysis. I know there's a lot going on the screen, but let's just pick one. This says RD2, so that's the planar array efficient solar cells. So they're saying actually you're going to be able to observe much more information. RD2 direct to geo. That means you don't have to be dropped off by a spaceship. You can have electric propulsion to go you up there. So all of these different things, you can see the levelized cost of energy in almost all of them, honestly, is far, far, far above any other sorts of clean energy. It's above geothermal, it's above concentrated solar power, it's above hydropower, it's above theoretical costs of nuclear fission if we get SMRs really right. And the only two ways it could be cheaper is maybe if everything goes according to plan. And that to me is very unrealistic. And so what they conclude is basically that because space-based solar power cannot deliver electricity cheaper and constantly than something like nuclear fission, it has no benefit in really the short or the medium term. And this paper like essentially trashed all the investment that has been happening in space-based solar power because they said, look, it's basically unrealistic that we will be able to provide what in energy terms we call baseload energy, so constant 24-hour energy, at anything like what it might be for geothermal. And so I just want to give you a couple quotes, both from that paper and from other papers that discuss space-based solar power, so you can understand what people think is the role of space-based solar power in the energy system today. So this is a paper from Caltech, the optimistic projection for an ample supply of pure baseload electricity. It's very important. Derived from space by 2050, it's substantiated by delirium. So this is their paper analyzing what pure baseload electricity will be by 2050. I'm going to show you what all of their estimates are later. This is Cash 2019. This is a paper from the UK government. Cassiopeia, this is the UK government's design for space-based solar power that they put about $1 billion into developing. The unique beam steering capability facilitates baseload delivery from alternative closer orbits with the possibility of single payload delivery. And then finally, that NASA paper, we compare space-based solar power systems to other baseload renewable energy production technologies, as well as nuclear power. And so, like across the board, when people look at space-based solar power and they say, can this add value to our electricity system? The question they're asking is, can we deliver baseload electricity 24/7 in one place at cheaper than the alternative? And the answer is like almost universally no. There's a few startups that think they can, but I'm somewhat skeptical. And so then the question I've been asking, and this now gets to the meat of the paper, is it right to think that the goalpost for space-based solar power being like creating value on the grid, is it actually baseload electricity? Or is it possible that there's something else that could happen here that would allow you not at 2 cents or 4 cents or even 15 cents a kilowatt hour, but still to create value on the grid, given everything I've been saying about the need for electricity and this problem of rising renewable energy correlating with rising costs of electricity. And so what I say is that the cost of firming, which is that, you know, all those backup costs, building in the backup markets, capacity markets, the gas peakers, that's the marginal firming cost per kilowatt hour. P is the space-based solar system capacity. U is the utilization rate, so how much you're using your system. T value is the amount of total value you'll get from avoided firming costs. And there are 8,760 hours in a year. Basically, what I would posit is that you actually don't need to be giving baseload power to be valuable, because if you can save money on firming costs, you can save money on the backup. You can actually create value on the grid today, even if you're generating electricity more expensively than, let's say, terrestrial. So if you multiply, you know, the marginal firming costs, how large your system is, how much you're utilizing it, and the amount of hours in the day, what you will get is the total value you're saving the system by not having to pay for backup power. And that's because if you could direct your space-based solar power to solar fields on Earth that are not currently generating, you can basically turn intermittent photovoltaic solar power in your terrestrial PV into 24-hour baseload. And so that would mean that like 4 cents a kilowatt hour, that would be not intermittent, but that would be constant. And so you wouldn't have to pay for those long duration batteries. You wouldn't have to pay for firming costs. You wouldn't have to pay for gas peakers or capacity markets. And what I'm trying to figure out is what is the value of offering that service? And then I take an example, a 2 gigawatt system with a 95% capacity factor um, would get you $80 million a year of saved firming costs if you were able to basically turn your terrestrial solar that you're shining your space-based solar power onto into 24-hour power instead of intermittent power. Um, I just want to I will get back to this in the end, but I want to make sure this is really, really clear. So what I'm saying here is basically that how are we using our space-based solar power arrays in orbit? Instead of having them shine on one point and viewing this as a new power station you're building that is 24 hours, you would adjust the beam to be on anywhere on Earth or anywhere in the continental United States, this is American. And you could do that in a highly elliptical orbit where you do not have your terrestrial solar power being generated by your power plant. And so you would basically turn your intermittent solar field into a form of baseload power. I then went through and I've looked at all of the techno-economic analysis out there that have happened in the last 5 years. There's, about 13 of them. And I compare the size of the systems that they've proposed and analyzed with the firming costs that will be avoided given that utilization rate and size. And then I've also looked at the LCOE. Now, what we get to is, if you can see it here, a lot of them are actually, once you subtract the firming costs, below the cost of gas, even if they are above the cost of terrestrial solar. And so this is quite an important point. So there are some estimates that say that the cost of space-based solar power, whatever happens, particularly in say somewhere like NEO, is going to be thousands of dollars per megawatt hour. So many dollars per kilowatt hour. And if this is correct, then they're basically right. This has no value. But there are a lot of projections, including those by NASA, that are actually relatively realistic, that fall into this very narrow band, where they are much more expensive, double or triple the cost of terrestrial solar, but they are still cheaper than gas peaker plants, and they can still actually deliver value by avoiding firming costs. And so what I'm really talking about here is the goalposts of where we need to get to in our expectations of LCOE, of levelized cost of energy for space-based solar power, for it to have value. And with a couple exceptions, I actually think that, and you can go through the papers and see the assumptions they make, a lot of these fall roughly in this range. And so if we are able to view space-based solar power as flexible and dispatchable, in other words, playing the role of a gas peaker plant in the grid, or replacing the need to build transmission lines and batteries, rather than as a form of baseload power, this might actually have, in the medium term, let's say 2035, real value for the grid. This relates basically to utilization. So the more you utilize your asset, the greater the value is, because you're avoiding more and more firming costs. So if you are constantly shining somewhere on Earth and making a receiver create electricity that would otherwise not be, then the avoided firming cost goes up. So this is just basically a sensitivity analysis of utilization versus avoided firming cost. So there's a kind of a lot more technical analysis to lay behind the previous graph, but I want to get to the policy implications. As I mentioned, there's billions of dollars being spent both in public and private money on space-based solar power. But I think, in my mind, the fact that you have a much more realistic chance of creating value with space-based solar as a flexible resource has a few policy implications. First of all, we should be focusing on types of space-based solar power that have dynamic beam steering. It basically means you can move the beam relatively easily to different spots on Earth. Delivering power where and when it is most valuable requires systems to redirect to disperse rectangles or solar farms, necessitating phased array microwave or laser transmitters with fine control on autonomous alignment. That basically means, like, for example, of those two designs I showed you from NASA, only the heliostat one will allow you to do that, because you can move the beam much more easily. Second, you want an orbit which has very, very high utilization. So particularly the architectures in geosynchronous orbit, to some extent uh, middle, these achieve much, much higher utilization than low Earth orbit or highly elliptical orbits, which are really focused on highly elliptical orbits are trying to focus on only covering one spot and always covering it, rather than being able to cover, let's say, 60% of the Earth, like in GEO. Um, and then LEO is to basically be able to track. So there are a few different space-based solar companies out there, as I mentioned. The ones that have actually received the most funding are putting their satellites in LEO because they want to be able to track military assets. And so these are basically being used for like off-grid military applications. And there's a couple in highly elliptical orbits because they want to basically create a power plant. And so they need to be at 24 hours over it. Whereas if you want to be able to use dynamic beam steering, you want to be in probably a geo orbit. And then finally, ground system prioritization. Dispatchable delivery is most valuable during periods of high marginal cost or reliability stress, as well as those with dynamic pricing. Those offer the highest value creation for space-based solar power. Dynamic pricing is when you can basically charge more for electricity when there's a lack of supply. And so if you're able to integrate into grids that have dynamic pricing, i.e. changing pricing depending on supply and demand, you can then obviously create more value. And then my final slide, this is just basically my conclusion. What I say is that it's currently not feasible as a competitor to the lowest cost generation. Existing architectures are an order of magnitude too costly, and they also rely on technologies that are unproven at scale. So I think NASA's 2024 analysis is very true that realistically, this is not going to become the cheapest form of energy generation anytime soon. However, with some very realistic assumptions, not even all of them, not the kind of the best case from that NASA analysis, but for example, work on electric propulsion to switch orbits, or relatively realistic falls in the cost of launch to match kind of SpaceX's expectations, you can get to LCOEs below 20 cents, maybe even 10 cents. And while that isn't the lowest cost form of generation, that does become cost competitive with flexible generation, so with gas, and it creates value for the energy system in the medium term, especially given the problem we have with the increased costs of integrating variable renewable energy. So yeah, that's basically the core point is if we think about space-based solar power from the perspective of what we actually need on the grid, given the increased pressures for electricity use and decarbonization, looking at how we can actually design these architectures, given that we're relatively early on in our kind of journey to building these, doing them in such a way that they can actually be flexible. So dynamic beam steering, high geosynchronous orbits, and then thinking carefully about which ground stations we do. That could actually make space-based solar power really valuable for the terrestrial energy system in the, let's say, the medium, if not the short term. So there we go.
Thank you. Thank you so much, Eli. Thank you for bringing this topic of solar energy into this seminar. I see there was quite an activity while you were speaking, so I will try to get the actual questions from the comment section, and maybe Tony will help me with releasing the ban on the mute button for the people who asked questions. So I see that Dr. Lal had a question. Actually, I see that you have two, so you might as well just ask them both in one shot to Eli. One has to do with SpaceX, and the other one I think is comparing the cost with SMR.
Hi, the video turned on. Hi, Ela, that was amazing. Thank you so much. Yeah, my questions are based on some research I've seen. SpaceX has a lot of self-traffic, self payloads for Starship, including the continual renewal of Starlink satellites. So I wonder if there's any evidence that the prices would drop as low as we all think, right? So it isn't just you. I mean, I've seen this everywhere. And it's a pretty, I just worry that putting all of our eggs in this low cost may get us in trouble. There is no competition, right? I mean, until there's actual competition, SpaceX, I mean, they're a private sector company, they won't drop the prices. And the second one is, cost competitiveness. Somebody mentioned, that forward basis, and the military may not care about high cost, high price. And my question is, even they would compare with other things like, Pele, which is a small modular reactor or microreactor. Army is funding, and there's other efforts on military, power for military bases that are nuclear.
Thank you very much.
Over.
Great questions, and nice to see you, Bhavya. On the first question, I think that almost everyone on this call probably knows more about the answer to what SpaceX can do with their prices than I do. I'm coming to this from the energy world, and I think you Bhavya, I would trust you to have a better view than I would. What I would say on that is actually, like, when we were working on putting together like a big consortium of the US-based space-based solar companies through Harvard to like figure out kind of what kind of moonshot policies would be needed to get the administration to, let's say, reach a 2030 megawatt hour delivered or something like this. And so we were talking to the 3 or 4 space-based solar companies that are based in the United States, and their main concern was actually just about access to launch. So at least this is what they said, is that they were relatively confident that the price point that SpaceX has gone out with for Starship, so somewhere in the $150 to $250 a kilo for LEO range, they think that is probably what they're going to charge. Obviously, they're a monopolist, so they could end up probably double that, and they wouldn't have any less demand. But their concern was actually much more about they do not think that there would be enough launch to service the demand. And so one of the things they were like keen on is trying to, for example, as a policy matter, guarantee launch services for space-based solar power pilots, as well as much more profitable telecoms. But I think like it's a really fair question. I have honestly no idea what is going to happen to the price point SpaceX have supplied. On the SMR point, well, like this is like a whole side question, so I won't spend more than 30 seconds, but I love talking about nuclear energy, which is that I've seen a lot of incredibly optimistic projections for the decline in costs of nuclear energy. I personally would love SMRs to get to 10 cents a kilowatt hour, 8 cents a kilowatt hour. Some of them are presenting 5 cents a kilowatt hour. I just think it's basically impossible. So almost every SMR design I've seen is basically a smaller version of the AP1000 Westinghouse, the original design that we built in the United States, and then several other countries stole the design of. And the hope is that if you produce thousands of them, you lower yourself down a learning curve, like we did on solar with manufacturing. So like humans are really, really good at manufacturing learning curves. And if we produce things a lot, we get really good at producing them. But I think the problem is that like the things that drive up nuclear power costs are really very rarely actually the cost of manufacturing the reactor. They're the fact that like these projects overrun by 10 years plus. They're all the like other stuff that goes into the engineering of installing them. And all of these reactors are light water reactors based on the AP1000. And so I don't see that those costs, which are actually the majority of the cost of building a nuclear reactor, are going to be able to go down just because your reactor is smaller. So I don't, unfortunately, see the chances of SMRs like falling certainly below 20 cents a kilowatt hour, if not 10.
Interesting. Thank you. And I see that Mehdi, you had a comment about boundary conditions. Would you like to make that comment? No? Well, if not, I'll just move to the next comment and we can get back to you. Caris Cosmas, you were mentioning something about using lunar material. Do you want to make that? Yes.
So was this
Would you
Mehdi's
like to make
comments?
that comment?
I can read the content.
Hi, thank you.
It's a calculation coming from spaceflight dynamics that the kinetic energy that is needed for launching something from the lunar surface to geostationary orbit is 22 times less than launching the same mass from Cape Canaveral, for example. And given the fact that the orbit of choice for space-based solar power seems to be the geosynchronous orbit, the question is, has anybody updated the existing studies with the assumption that the material are coming from the moon instead of launching those material from Earth?
So the mechanical answer to your question is no. No one has done that. I would be it doesn't seem like a short or even a medium or even really long term prospect to me that it would be cheaper to make photovoltaic cells on the moon and then launch them into space from there than to do it from Earth. That feels like maybe ultimately possible, but if we're talking about like solving the problem of data center electricity usage in the next 10 years, like the level of engineering that would be required on the moon when we can't even get a man there, that feels like pretty phenomenal to me. I think like if we're talking about what the energy system looks like in 2100, I can see what you mean in the like the highest cost of any of these systems is pretty much always getting it off the surface. But yeah, I think like a real manufacturing base on the lunar surface feels pretty far off.
But nobody has done the exercise.
No, not that I know of. I would love to respond very briefly to someone put an excellent Maddie put an excellent question in the chat, which is basically like this is basically responding to the fact that we cannot store energy cheaply. Like this is the real problem with variable electricity sources is that long duration batteries are just unbelievably expensive. And so we can now roughly economically store like it's called diurnal systems. So like it's kind of okay that your solar power only generates during the day and then doesn't generate at night. We can kind of smooth that out with batteries. I showed you that chart. You go from, let's say, 4 cents a kilowatt hour to 12 cents a kilowatt hour. But if you're trying to smooth out a seasonal type storage, we just do not have long duration batteries that are anything like cost effective. And so I think the question, they call that a boundary condition, is like, if we got really, really, really good at long duration energy storage, or if we built incredibly long transmission lines. So if you had transmission lines linking, let's say, the northeast of the United States with California, because the sun is always shining somewhere in the United States, that would probably solve the problem. So I would almost think of this as like, what do you have more faith in? Our ability to be kind of innovative in engineering of space technology, or Congress to pass comprehensive reform of transmission planning in the United States. And unfortunately, my bet is kind of on the former. But it is true that like my arguments would basically dissolve if we had a functioning single transmission market in the United States, or if we had really cheap long duration energy storage. And I think that's a great point to make from Maddie.
Thank you. Alessio, I see that you had a question about military applications. Maybe you would like to ask them several questions.
Yeah, there were several questions on military. I only had one, which is, to the best of my knowledge, technologies, including energy technologies early on, historically, are more expensive and often have had military applications because that is a sector where costs are less of a concern. And I've read somewhere that this technology could be used for military applications as well because it allows you to bring energy far from home. Is this something that you have considered as one of the potential initial uses that would allow a scaling up and therefore a reduction in costs?
Yeah, totally. So it's a great question. I was told when researching this, so one of the foremost companies working on this is called Etherflux, and it was founded by the founder of Robinhood. And I had a long conversation with them, and their like go-to stat is that the military pays something like $400 a gallon for diesel deployed to its forward operating bases, because they have to drive the diesel out to these very remote places in Syria and wherever it is. And so their initial contracts and the way they're thinking of their customers for space-based solar power is like, if you can deliver 24-hour electricity at less than $400 a gallon for your generator, like they're delivering diesel for that cost and putting it into a generator, which is probably like, I don't even know how much, probably in the hundreds of dollars per kilowatt hour. Then you can actually create value because your forward base would not need a generator that gets to diesel. It would need a rectenna that receives microwave radiation. So that is exactly their like go-to-market business plan. As an investor, that is like a very interesting way of proving out your technology, maybe then demonstrating it, moving down a learning curve, etc. I guess I'm thinking about this from the perspective of the energy system. While useful to militaries, that is like yeah, it's an interesting commercial application, but doesn't really have widespread use. If you see what I mean. So I think basically your instinct is completely right that like yes, this has very clear advantages if you're willing to pay almost unlimited amounts of money to have a secure energy supply anywhere in the world. Which is also why, like, you know, people have said that we have a real problem with building nuclear energy in this country, in America. Well, actually, like, we're really good at building nuclear reactors for subs and for aircraft carriers. You never have to refuel an aircraft carrier. It's just that they're delivering energy at like $400 a kilowatt hour. And so it's not relevant for commercial use.
Mm. Thank you. And moving to Bernard, he made a comment about the target markets such as polar stations, small island nations. Would you like to make that comment or add a question?
Yes. So I thought, because I did my master thesis on space-based solar power economic side, and there was one point of this military markets as an early adopting market, and the second part was off-grid markets, like when you put such a satellite into polar orbit above such polar stations or other markets, they're off-grid, where it would be very cost heavy to install all this grids stuff and all this normal traditional infrastructure. It would be very expensive, and so you could add up the cost of space-based solar power with this kind of installation costs, and therefore saving money, like economic wise.
Yeah, you're totally right. So this might not be the case anymore, but when I was a few years ago, I know that the most expensive electricity in the world for retail customers was in the Comoros Islands, and the average retail electricity price there was something like 60 cents a kilowatt hour, which is crazy for one of the poorest countries in the world. And so I think you're totally right that there are probably, as well as military applications for off-grid communities that are currently basically using diesel generators or island countries. I guess my motivation is like really what is the use of this in an advanced economy, particularly the United States. But I think yeah, you're completely right that there are really obvious kind of pockets of demand where people are paying a lot for electricity, mostly because they need to get diesel to a generator in a remote part of the world.
Thank you. Luisa, I see that you also have a questions about the cross-border transmission and regulatory approval. Would you like to ask your question?
Yes. Hi, Joanna. Thank you really for your presentation. I have a couple of questions. First, I'm curious about this issue. So basically, SBSP implies that there will be a transmission of gigawatt scale energy across multiple national jurisdictions. So do you envisage which type of implication in terms of cross-border transmissions, also in terms of regulatory approval? And secondly, my other question is concerning whether there could be the emergence of a space grid market where there are like orbital operators that could be linked to the even to large companies like SpaceX or Virgin that maybe they switch their economic interest into this specific area where they sell dispatchable capacity into multiple regional grids. So do you see the possibility of the emergence of this space grid market that can attract, commercial space ventures?
That's great. On the regulatory point, I honestly have no idea. I think one of the key problems that in Europe, they've been trying to build an interconnection from North Africa into the European grid for the last 30 years. First, they were going to go to Spain, and then we were going to go to the UK, and then we were going to France, because if you could export electricity probably from Morocco into Europe, again, you basically solve all of these dispatchability problems. There's an engineering challenge there, which is like laying a transmission line. But there's also a huge grid balancing question, which is once you've connected these two grids, you have to have them balanced. In some ways, this becomes a lot easier. Like the regulation is, I mean, I guess it's microwave energy, so it could theoretically be recognized, but you're basically just providing energy from space. So I have no idea what a regulatory framework would even look like and what it means to be kind of doing cross-border work. Like as you probably know, like legally speaking, any satellite is owned by the launching state, and the launching state in the outer space 3D is not like very tightly defined. It's either the one supervising it, or it's the one of the nationals of the company, or it's the one from which it launched. So I basically don't really know the answer. And if you have any thoughts on it, Lisa, I'd love to hear. On the market, yeah, eventually I think that is what at least the few folks I've spoken to in the White House have envisaged, which is that you could have a really thriving market for dispatchable power from space. Yeah.
Thank you. And Martin, you were asking about the effect of space debris on the systems. Would you like to ask your question?
Yes, I don't know if you can hear me correctly.
Yes, we
Yeah,
can.
okay. Yeah, my question was regarding there's a growing number of mega constellations, and I was thinking about having solar panels in space. Perhaps it would like even increase the risk of collision in space, because I mean the whole point of solar panel is to have a um, big surface. So I was thinking about will it have some problems? Yeah, will leave some problems? Yeah. Thank you.
This is great. So these are huge. I didn't really get into that in the presentation. Both the solar panels themselves and the ground stations you need are like really big, like kilometers wide. In terms of space debris, so as I said, like in order for this to be effective, you kind of want it to be in geosynchronous orbit, because you can then cover more of the Earth, which has pluses and minuses for space debris. In that, like that's 36,000 kilometers in the air, and so that there's so much space there that actually, it's really not congested at all. And so at the moment, I don't think there's any worries of congestion, as far as I know. People on this call might correct me in geo. But at the same time, it's a much narrower band of potential orbits, because you need to be like pretty much exactly 36,000 kilometers above the Earth. So I guess it does create the risk of space debris. These are also like relatively easy to track. I don't have a good answer. Like it's definitely something to be thought about, but it sort of goes to the entire space economy. And I assume that everyone on this call is interested in a thriving space economy. So I think it's something we're going to have to figure out for everything we put up in space.
Thank you. Space
Thank you.
power actually has related questions regarding some technical specifications about this. Basically, the receivers and the rectangle. Would you like to ask your question? Hi.
Yeah, please. I've got two. I just wanted to follow up on the other one.
I don't think I'm gonna interrupt you for
The
a
solar
second.
radiation pressure as well would be.
I'm gonna interrupt you for a second just because we don't hear you very well. So if you like, I'm going to read out your question so everybody.
Okay.
It's just I don't hear it very well. I'm sorry. So how does the flexibility requirement preference affect location for these antennae? My current understanding that it's either that the receivers have to be big kilometers square range, or the beam needs to be very narrow, increasing the power density and the risk of damage and health.
Yeah,
Eli,
that's definitely
did you
true.
see that?
Yeah,
Thank you.
completely true. So what we assumed in the paper is that you basically co-locate your rectennas with existing solar infrastructure, because then you can use the transmission interconnection. And so sometimes those have to be larger, as I mean, knowing what you do for a living at Space Power. As you know, these are not like super invasive structures, so you can basically put them over things relatively easily. So when we were looking at where we would have recommended putting the sites, we basically say you should co-locate them with large scale, let's say gigawatt scale solar arrays.
Thank you. And I'll take a last question. I'm sorry that we are not able to get through all of them, but we like to be on time. And so, Harold, you are mentioning a Delphi study on the future of space economy, and you have also a related question. Would you like to ask that? No? Well, if that's the case, I'm going to move on. And WH has a question about the minimum efficient scale for space-based power relative to hyperscaler data center. Would you like to ask your question, or I'm just reading it?
Sure. I've just Ward Hanson, that's WH.
No.
So yeah, the question was, do you have a sense of the minimum efficient scale? The previous questions sort of got to, because the local congestion of the grids are being driven, as you said, by some of these massive data centers. So some of the early high value uses could be to alleviate intermittent pressure at those spots. So are they of the same magnitude?
Great question. So I was basically going on chatting to people that are doing this and then reading everything I could find about the papers. I'm not actually in the field, so maybe the guy from Space Power can answer as well. Almost every paper that's analyzed this assumes a 200 megawatt pilot, and then there's a couple that assume that the steady state size of the beam will be 2 gigawatts. So that is just that is the assumption I've seen in the market. I haven't seen much justification for why that is, but the assumption seems to be, and this is what, for example, NASA's analysis of it is, and also the UK Cassiopeia concept is a pilot of 200 megawatts and then a full scale array of 2 gigawatts. 200 megawatts would probably be smaller than your average data center. 2 gigawatts would be one of the largest. Yeah. I think technically speaking, OpenAI have now announced they're going to have a 3 gigawatt data center, which is a colossal amount of energy. But I can't think of an a priori reason why you wouldn't be able to just scale relatively quickly, apart from things like limited cost of launch and stuff. But basically, the size is those are the orders of magnitude that people are talking about when they're doing these techno-economic analyses. Okay. Which again puts it roughly on par per system with the data center.
Right. Okay.
Thank you very much. Thank you very much, Eli, for such a thoughtful paper, and to everyone for writing so many questions in the chat. I'm sorry I wasn't able to get through all of them. I want to say that the next seminar is going to be November 18 at the same hour. We have our first practitioner talking next month. Her name is Karen Niemann Metcalf. She's an adjunct professor at Tallinn Law School, and she's going to talk about who owns the moon, stars, and orbit. And we thought it might be a good idea to put at least one practitioner among academics to talk about certain issues in space, and this time ownership it's going to take front stage. Thank you again for attending, and as I mentioned, it's very important that we have so many attendees and so good the papers, because as I mentioned last time as well, this is a pilot session, so to have a second season next semester, we will have to keep up both the attendance and the quality of the papers and the presentations. And I want to thank again Eli for such a great presentation. And I just want to ask at the end if Niha or Mattia would like to add something. Niha is our co-organizer from HBS, and Mattia, he is my colleague from ESPI. If you have anything to add, if not, we're just gonna.
No, I just put in the chat. Thank you very much for all joining us. Incredibly stimulating, and looking forward to the next session. Thank you.
Thank you.
Thanks, everyone.
Likewise from my side, thanks to everyone joining, and also for the great conversation in the chat, but also above all to Eli for the wonderful presentation and very, I would say, thoroughly researched area that is, I think, where there's still a lot of mysticism around. So I think demystifying that was really really important, and I think there's much more to be done in the future for sure, both on the economic side and on the technical side.
Great.
Absolutely.
Bye, everyone.
Okay. Bye, everyone, and see you on November 18th.